नमस्कार दोस्तों. So today we are going to revise D and F block elements through GSET questions. Okay. So first question from GSET 2002. The most important mineral for isolation of lead. So nobody denied that it is galena. Most important mineral for isolation of lead is galena. It is actually PBS. It is also called lead glance. Okay. So right option is galena. So what is anglesite? Actually anglesite is lead sulfate. Anglesite is lead sulfate. It is the oxidation product of primary ore, that is lead sulfide. Okay, what is cerussite? It is actually lead carbonate. It is also ore of lead, but it is not most important. Only 77.5% around lead is present in it, but it is not most important. Most important ore of for the isolation of lead is galena, lead sulfide. Morphite. Pyromorphite is actually lead chlorophosphate, and sometimes it is also mined for the isolation of lead. Okay, so first question, its answer is actually galena. Most important ore of lead is galena, keep in mind. Okay, now come to the question number 2. Which of the following lanthanide forms most stable divalent state? Cerium, samarium, europium and thulium. So these are all lanthanoids. So just write lanthanoids. So these are lanthanoids: cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, ytterbium and lutetium. Okay, so electronic configuration for the first one is 4f1, 5d1, 6s2. Praseodymium, it is 4f3, 6s2. For neodymium, it is 4f4, 6s2. For promethium, it is 4f5, 6s2. Samarium, it is 4f6, 6s2. For europium, it is 4f7, 6s2. Gadolinium, it is 4f7, 5d1, 6s2. And terbium, it is 4f9, 6s2. For dysprosium, it is 4f10, 6s2. Holmium, it is 4f11, 6s2. 4f12, 6s2. 4f13, 6s2. 4f14, 6s2. and 4f14, 5d1 and 6s2. So if you know the electronic configuration, you can easily determine which of the following is most stable in +2 state, divalent ion. So see the europium, after losing 2 electrons, it has exactly half-filled configuration, and ytterbium, after losing 2 electrons, it has fully filled absorption. That means europium and terbium both have most stable 2+ state. Okay, that means cerium, you know, its most stable state maybe +4. General oxidation state of all lanthanoid is +3. So europium is one of the example. That means europium is the right option. Okay, so for the second, divalent state is most stable for europium out of these elements of lanthanoids, right? Okay, now come to next. Zinc 2 compounds are generally, so you know, zinc is 3d10 4s2. That means zinc in 2+ state is 3d10, means fully filled d orbital. So no dd transition, no dd transition in zinc 2 plus compounds. That's why it is white in color. It is colorless, or we can say it is white. Zinc compounds are generally white, right? Okay, which of the following compounds is used in the hydrogenation of alkenes as a catalyst? So you know, for hydrogenation of alkenes, we use Wilkinson catalyst. That is chloro tris triphenyl phosphine rhodium 1 chloride. Rhodium 1 chloride. That means tris chloro tris triphenyl rhodium 1 chloride. So that means D option is correct. Done. So these are first four questions from D and F block elements. This question came in GSET 2004. Third question comes in GSET 2003, and first and second in GSET 2002. Okay. So keep in mind that Wilkinson catalyst is used in the hydrogenation of alkenes. Okay. Next question. Fifth question is from GSET 2008. Slag in iron extraction contains. So you know, main impurity in iron ore is, yes, tell me, which one is the main impurity in iron ore? Can you? So it is actually silica, and it should be removed, otherwise it can block the furnace. Okay, so silica is removed by reacting with calcium oxide, and therefore calcium silicate is formed in liquid state and float over the molten iron, right? So that means slag formed is calcium silicate. So this is impurity, acidic impurity, and calcium oxide as a basic flux, and that leads to the formation of slag. So slag in iron extraction contains calcium silicate. Okay. Next, the zinc group elements are called zinc, cadmium and mercury. Noble metals, coinage metals, volatile metals, or precious metals. So keep in mind, zinc, cadmium and mercury have fully filled d substitution, and that's why they have weak metallic bonding. As there is a weak metallic bonding, that's why their boiling point and melting point is low. That means they are volatile in nature because of weak metallic bonding. That's why they are called volatile metals. You know, noble metals, coinage metals, precious metals, they are almost synonymous. They are almost same because noble metal means which is resistant to corrosion. If it is resistant to corrosion, it is used in, historically they used in coins, you know, copper, silver, gold, group 11 elements all are coinage, even platinum, palladium, iridium, osmium. Okay, these are all noble metals. Copper, silver, gold, you know, they are used as coinage metals, and all obviously if they are resistant to corrosion, they are precious metals. And you know, iridium is used in spacecraft iridium or other metal. So means, you know, copper, silver, gold, palladium, platinum, iridium, osmium. Okay, these metals are noble metals, these are precious metals. Okay, or even they are copper, silver, gold are coinage metals. These are group 11 elements. Okay, so group 12 is volatile metals, group 11 are coinage metals because they are historically they were used to form coins. Even today we get coins of gold and silver. Okay, now atomic and ionic radii decreases from lanthanum to lutetium, and that is called lanthanoid contraction. Okay, and it is because of poor shielding of F electrons, and F electron anti-penultimate F electrons. Why they are poor shielding? Because their shape is diffused. Okay, and at the same time nuclear charge increases from lanthanum to lutetium. That means mutual shielding effect of N-2F electron is very little. That's true. Shape of F subshell is very much diffused, right? Nuclear charge increases. So these are the three reasons for lanthanoid contraction. Okay, that means all of these is the right option, and this question came in 2011. Okay, then transition elements form alloys. So you know, alloys are formed by those metals which are nearly of same size. Size should be same because you know, in alloys one metal atom is substituted by other. That's why size should be similar. If size is similar, they can easily form alloys. Okay, that's why transition elements, they have almost similar size. That's why they are used to form alloys. So C option is correct. This question also came in GSET 2011. Okay, so these are the questions from GSET 2013. Ninth question is, which of the following is the most general property of all the transition elements? So you see, they are all metals, they are occur in variable oxygen state, all are paramagnetic, all form complexes. First of all, these are all general properties of transition elements because they are all metal, they are metals, they occur in variable oxygen state, they are paramagnetic, they form complexes, but word is all. This word makes the difference. Actually, they all occur in variable oxygen state, wrong. Most of them occur in variable oxidation state, and scandium is an exception. Scandium occurs in only +3 state. Okay, most of them are paramagnetic, but all are not paramagnetic. Most of them form complexes, but not all. But it is for sure that they are all are metals. All are metals. That's why this is the most general property of all the transition elements. Okay, next, amongst the following divalent ions, which will show strongest paramagnetism. So paramagnetism So paramagnetism is proportional to number of unpaired electrons. Okay, so you see in first case D5 is there, here D3, D9. In first case, how many valence electrons are there? 5. See, this is the D subshell in which there are 5 orbitals. D3, there are 3 unpaired electrons. In D5, there are 5 unpaired electrons. In D9, there are, now pairing starts, there is only 1 unpaired electron. So maximum number of unpaired electrons are in first case. So this is the right option. Simple. Okay. Question from GSET 2013. In the oxidation of ferrous sulfate by acidified KMnO4, the typical Lewis base is. So when FeSO4 react with KMnO4 in the presence of sulfuric acid, ferrous sulfate changes into ferric sulfate, potassium gives K2SO4, manganese gives MnSO4 along with water, right? So what it means, ferrous Fe2 plus changes into Fe3 plus, that means oxidation takes place. And what is Lewis base? Lewis base means which can lose electron. So Mn2 plus, here it is +7, it is +2. So it is not a Lewis base. Fe2 plus changes into Fe3 plus. So obviously Fe2 plus loses 1 electron to give Fe3 plus. That means Fe2 plus is typical Lewis base. Otherwise H plus, here it is +1, here it is also +1. Potassium, here it is +1, again it is +1. That means there is change in oxidation number of Fe2 plus to Fe3 plus. Mn changes from +7 to +2. Okay, so it is only Fe2 plus which lose electron to give Fe3 plus, right? So right option is B. Next, lanthanide ions are colored. Now say lanthanide ions are colored due to FF transition, and that FF transition takes place in visible region. Now, which of the following ions is colorless? Values in brackets indicates are available electron. See, 4 means here it is 4F4, it is 4F5, it is 4F6, and this case it is 4F7. Obviously, there is only one which is exactly half filled, and when exactly half filled 4F subshell, it has extra stability, and as it has extra stability, its electron is not excited in the visible region. Okay, so that means this ion is colorless, or compound containing this ion is colorless. Okay, so gadolinium 3 plus, because of exactly half filled configuration, it is colorless, because electron is not excited in the visible region, maybe in a UV region it can be excited. Okay, so right option is D. So next questions, 14 and 50 questions came in 2013, they are repeated in 2011 and 2004. Question came in 2004 and 2011, that is repeated in 2013. These are the two questions. Fourth question we have done, seventh question we have done. Here they are questions from 2013. Okay. Now next, these are the questions from 2014. Calomel is, now first A option, K2HgI4, potassium tetrahydromercurate 2. This is, what is this? Alkaline solution of this is what? Nessler reagent. Alkaline solution of K2HgI4 is Nessler's reagent used to detect ammonia, that you know. So this is the Nessler reagent, but calomel is a component used in reference electrode in electrochemistry, and that is mercurous chloride, Hg2Cl2. Okay, right? Now that means B option is correct. The property not shown by transition elements is that variable oxidation state, most of them have variable oxidation state with exception like scandium. Act as catalyst, yes, most of them act as a catalyst and their compound as well. Paramagnetic in nature, most of them are paramagnetic in nature. All imparts color to the flame. That's not true. You know, all do not impart color to the flame. That you know better. Okay, so this one is wrong, because flame test is not for all transition elements, though it is useful for alkaline earth metals, alkali metals, okay, but it is not good for transition elements. All transition elements are not detected by flame test, so this is not true for transition elements. Okay, so these are the questions up to 2014. Thank you very much for watching this video. This is the first part of D and F block elements.